It starts off with this. And before I even explain to you what you see here, what's important is why we're doing what we're doing. So up until now, we did field lines or electric fields of a point charge. Okay, so a positive charge has field lines going radially outwards. A negative charge has field lines going radially inwards. But that's not. It's easy to calculate for a point charge, but nothing in real life is really a point charge. Okay, unless you have electrons and protons, but we in our daily lives don't really deal with those unless we're like super scientists working in CERN on like a particle accelerators and things like that. So we need to also understand the more common uses. For example, the electric field produced by a wire or the electric field produced by a plate. Right? So these are all super relevant applications of what we're doing today. And so it's important to understand this. If I gave you a line, don't look at the picture that's here, but if I gave you a line here, all right, you see it at the top. If I gave you a line and I said this is a wire, and on this wire there is charge, and every centimeter there is 1 coulomb of charge, right? So there you go, there's your wire. Let's call it 20 centimeters, right? And I said every centimeter, there is a line. Every centimeter, there is 1 coulomb of charge. What could you tell me about this wire? What is the charge of my wire? 20 coulomb. Yeah, exactly. What did I give you? What information did I give you that was able to allow you to determine that the charge of the wire was 20 coulomb? 1 coulomb per centimeter, all right, and the total length. And how did you find the answer with those two? We'll multiply the total length. So that 1 coulomb per centimeter, what do you want to call that value? What do you call the 1 coulomb per centimeter? Melanie? Yeah, exactly. So in our case, we're going to call that charge density. All right, and that's basically how much charge an object has per unit size. Okay, so in a line, the size is length. In the area, what do you think that might be? Yeah, so area, all right. On a 3D object, what might that be? Volume, exactly. Okay, so it's charge density multiplied by either length, area, or volume. You don't need to write that down if I have it written in the next couple slides. Yeah. Meters cubed if it's a cube. Right. Yeah. So in this case, we say we have something called a charge density. Is that written here somewhere? Yeah, okay, so we have a charge density, all right, and that charge density is going to tell us what the charge of this object is per unit length, all right, in the case of a line. So we have, I'm going to wait for this one. Everyone's okay with what I just explained? What was convenient about the charge density that, that Mark came up with? Or when you're looking at this rod, this one here, this wire rather, we're going to call it a wire just because it's not, we're not going to make it into a rectangle, we'll make it into a wire. What's convenient about this wire is that if you take any size object, so let's say you take a part of this wire, I'm going to take this part of this wire, the one I'm circling right now, and if I take any other part of the same size anywhere else on the wire, what could you tell me about the two charges? They're the same. Okay, and it's important in this case that we know that this is what we call a uniform charge density. All right. So at the bottom, let's write that a uniform charge density does not vary. So the charge density is the same all throughout the object. That's the very, very, very simple way of calculating this. Again, unfortunately, in real life, nothing is uniformly dense in terms of its charge. Everything has a non-uniform charge density, and that's where the complicated stuff comes into play. Okay? Let me ask you a question. This is how I'm going to lead into the integrals part. If I figured out the charge of one piece, right? How do I use that one piece to figure out the charge of the whole thing? Yep. Exactly. You sum up all the little pieces. There's a lot of glitching happening right now. You sum up all the little pieces. And if you sum up all the little pieces from one end of the wire to the other end of the wire, then you get the charge of the whole thing. That's basically what integrals are, right? You're summing up really small pieces of things until you get the whole thing. You guys follow what I'm saying? Okay? Here, I'm talking about what the charge density symbols are for the different types of shapes. So for a straight line, we have symbol lambda. For areas, you have sigma, and for volumes, you have rho. Are you guys all familiar with those Greek letters? Yeah. Okay. Rho is, just so you know, rho is spelled R-H-O. Okay. And again, that's charge per meter, or charge per meter squared, or charge per meter cubed. That's the charge density symbol. Okay. Sometimes it's uniform, sometimes it's not. All right. So in the case of a wire, we said that it's the charge density times the length in order to get the total charge, right? And an area would be the charge density multiplied by area to get the total charge. And finally, if you want to get the total charge of a volume, well, it's the charge density multiplied by the volume. Okay? So far, so good? Now we're getting into the integrals. So if I wanted to calculate a really small part of a charged object, right? So a really small part of a charged object, that's where the dq is, right? I need to know the charge density of that small area, that small part, and the length of that small part. And if I have those two pieces of information, I can find the charge of that small part. Okay? And if I add up by using the integral of all these small parts, I can find the total Q, right? If I find all the little charges and add them all up, I'm going to get the big Q, which is everything, right? All the charge of that object. That means I have to add up all the little charge densities multiplied by all the little lengths, all right, in the case of a long wire. So you end up with this expression here when it comes to finding the total charge of a wire. Yeah, Sean. Okay, absolutely. So you have a wire. If you find the charge of one part of it, and you add up all the little charges, you get the charge of the whole thing. So how do you find the charge of a little part of this wire? So you have that here. You multiply the charge density and that tiny place in that wire. All right? But now you have to add them all up. That's why we're taking the sum. This symbol here, this integral symbol, that's the add up symbol. Okay? Yeah, and when you add up all the little charges, what you end up getting is the whole charge. Okay? Otherwise, I mean, we could also look at this as the integral of dq is q. dq is the charge of a little portion of your object. The length of a little portion of your object. Remember when Mark said that he multiplied the charge density by the length to find the charge? Yeah. Exactly. And that's just for a small part. Okay, when you have a d in front of it, it's for a small part only. All right, but when you integrate it, that means you're adding all the small ones together. Yeah, no. Well, we're trying to solve for q. I mean, q can be a function. We're not going to deal with it, but q, yeah, it can be a function. Okay. Lambda, however, doesn't have to be always a constant. So in the case, in the example I did before, go back, we said that the charge density was 1 coulomb over 0.2 meters, which is 5 coulombs per meter. And no matter where you look at on this wire, the charge density is 5 coulombs per meter. So whether you're at the beginning, it's 5 coulombs per meter. If you look at the end, it's 5 coulombs per meter. It's the same all throughout. That, however, can be a function, and that's what we call non-uniform charge density. All right, so now that we know that, let's do one example, all right? And there is an integration to do in this problem, all right? But let's set it up together. So I have a wire, and I'm saying that if you take a small part of this wire, if I take a dl, small part of it, right, and multiply it by lambda, I should be able to get the charge of that small plate. But the question asks me what is the charge of the whole wire. So I have to add up all those small charges. So I'd have to do the integral of dq, right, so that I can get the charge of the full thing. And if I do the integral of dq, I have to do the integral of lambda dl. In this case, they use x actually, so let's just use x as well, if you don't mind. But x and l are the same thing in this case. Okay? But what's lambda? Lambda is a function. Look at that. It's a quadratic function expressed by 3 times 10 to the negative 6 x squared. So in fact, what I'm doing is, okay, now the integral of dq is just q, big Q, and now I'm doing the integral of 3 times 10 to the negative 6 x squared dx, right? And I want to know the charge of the wire between 3 meters and 5 meters. So those are my limits of my integral. So who knows how to do the integral of a quadratic function? Raleigh, what is it? Exactly. So which is what? 3? Okay, so it would be 3 times 10 to the negative 6, x to the 3 over 3 from 3 to 5. All right. How do I solve this? Now that I've solved the integral, how do I actually come up with a value for that integral using my 3 and my 5? You guys remember how to do that? Melanie? Yeah? Okay, exactly. So I have this function. I find the f of b, in this case the b is 5, minus f of a, in this case the a is 3. So it'd be 3 times 10 to the minus 6 times 5 cubed over 3 minus 3 times 10 to the negative 6 times 3 cubed over 3. That's going to give you, you have to give me a number, okay, you got a number? 9.8 times 10 to the negative 5. Did everyone get that? What are my units, Marco? Coulombs. Very good. Is this making sense? Did you answer me the question at the bottom? The only thing that I've changed is the limits of my integral, all right? So instead of it being from 3 to 5, it's going to be from 8 to 10. Tell me if I get a different answer. And we'll write it down at the bottom. Solve the integral the same way as you did. Give me a value with the limits being 8 to 10. Yep. Yep, what did you get? 4.8 times 10 to the units. Cool. So it is different, but why? Yep. Well, there's actually gain here, but that's not why. Yep. Okay, so if I were to graph this, all right, my function would be what as a function of what, and we're trying to find the area underneath it, right? Because we're doing an integral and the area underneath it. So we have charge density as a function of distance, so charge density lambda as a function of distance, and this is a quadratic function, right? And we took the area underneath the curve between 3 and 5, right, to find what the charge is, right? Whereas if we did this between 8 and 10 to find the area underneath here, 8 and 10, then the area underneath is a little bit different. So of course the charge is going to be more. All right, the area underneath that curve is more. Yeah. Why is the curve like that? Because the initial function is a quadratic function. Right? It's x to x squared. This is a non-uniform charge density. Yeah, because the charge density changes as a function of time. Yeah, if you want to write down this is a non-uniform charge density. Yeah. Not time as a function of distance. Yeah. Did I say time? Okay, I meant distance. Sorry, because mechanics you're always talking about time. Am I making sense? Yeah. All right. The next problem is where it starts to get very confusing. All right. Over here, I have a wire. The wire starts here and finishes here. So it has a length. All right. And I'm trying to find the electric field at point P, which is on the left of this wire, on the x-axis only. Okay? So this wire is going to produce an electric field. It has a charge of -4, so ostensibly it's going to be something like this. The electric field lines are going to look like that, right? We can't use the point charge formula, right? We can't just use KQ r squared, KQ over r squared, because this is made up of many different points all along this wire. It's made up of many different points that are adding to the electric field that's here. And these electric fields, I have to get further and further away from the point, they're getting weaker and weaker. So something is not the same, right? The electric field is not the same everywhere on that wire. So we have to add up all the individual electric field in order to get the full electric field. Okay? So if I were to do that, I would have to write the following. All right? So if I want to find the electric field, let's say right here, right, of that point right there, I need to find the distance in between the point that I'm looking for, so point P and there. So we're going to call, if this area, this distance here is called D, this distance here is called X, then this distance here is called D plus X. That part's simple. Any other question? No? That part's simple. Yep. I arbitrarily took a point. It will, but we're going to integrate so that we get all. Yeah. Okay. So we know that E is equal to KQ over R squared. All right. And here we already give you the charge of the whole wire. So we have Q. All right. And if I want to get all of them, right, I have to multiply my little dE, all right, of KQ over R squared. I have to multiply by all the little ones all throughout this wire. So I'm going to multiply that by dR. All right, and I'm going to call it dx, and you'll see why in a second. I'm going to multiply that all by dx. So if I integrate both sides, I got E is equal to the integral of KQ dx over R squared, but we said R squared is the distance between the point, this point here, and our arbitrary point, which is the function d plus x, all that squared. In this case, is k a constant? Is q a constant? So I can take those out of the integral, because it's one of the identities of integrals. So kq integral of dx over d plus x squared. That's an easy integral to solve, right? What are my limits to the integral in this case? Mark, what do you think? Minus 1 and 1, why minus 1 and 1? But I arbitrarily took that point, so you can't call that the middle, right? You can't call that the middle. Where does my wire start? 0. Where does my wire end? So those are the limits of my integral from 0 to 2. Do I have this value d down here? Is that a variable or is that constant? It's a constant. What's the value for it? 1. So in fact, even simpler, we have kq integral from 0 to 2 dx over 1 plus x squared. There we go. That's what I wrote here. And then now we just have to solve it. That's pretty straightforward. So the integral, the kq, or sorry, e is equal to kq p over x or over 1 plus x squared. That's the same thing as saying kq integral from 0 to 2 of dx, or let me just delete that. Oops, the highlighter. Of 1 plus x to the power of negative 2 dx. And that's just by the polynomial rule that you guys know. Can you guys integrate that and give me an answer, please? How do you integrate something to the power of minus 2? Melanie said it before. It's the same thing. So someone explain it. I'll remind you that before there was the integral of x squared dx. And she said that you have to add 1 to the exponent and divide it by that new exponent. So you x to the cube over 3. That's how we did it back then. So how do we need to do it for this one? Marco. Absolutely. So it'd be kq times 1 plus x to the power of minus 1. This glitch thing is annoying. I don't know how to fix that. The power of minus 1 over minus 1, which is the same thing as saying negative kq. I have to write my limits here from 0 to 2. It's the same thing as saying negative kq over 1 plus x. Between 0 and 2. Good grief. Okay. Can you evaluate that limit and then tell me an answer? Over backwards. So my answer should be 2 times 9 times 10 to the power of 9 times the charge, which was what? -4 microcoulomb, nanocoulomb. What was it? Microcoulomb times 10 to the minus 6 coulombs divided by 3, and that should give me my electric field. Can someone give me an answer? Yep. Minus 2/3 kQ. Oh, wait, where? Which one? This one here? It's, you have to do this one minus this one, right? So, yeah, that's right. So that's why I'm adding it here. You got it? Did someone punch this in? Give me an answer. How much? Minus 24,000? Newtons per coulomb. Yeah. Any questions about that? I'll wait until you guys are finished writing. Yeah. Electric field. Yeah. Okay. Now we're getting to the really tough ones. Again, bear with me. The hardest part about this one is setting up the integral. Once you set up the integral, it's actually not so bad. Okay, let's explain this problem and try to really understand what's happening. So a scientist finds a new element on a remote planet. The electron cloud distribution is a perfect sphere. Okay, so imagine that there is a sphere and there is electrons all throughout, and you want to know what the charge is of this sphere. All right, so it's in coulombs. You want to try to figure out what that charge is. Okay, so the model is as follows. All right, so it says here that the charge density, right? That's the Greek letter rho. They just use p here, but it's the Greek letter rho. So the charge density as a function of what is that? What is that r when you talk radius? Okay, so as you're getting closer and closer to the edge of the sphere, the charge density is changing. All right, so that's what we know. And big R here is a constant. That's the radius of the sphere, right? And this is the variable in that function, right? And this charge density only exists up until R, right? Up until you reach the edge of the sphere. And anything beyond the edge, well, there is no more charge density beyond that. Okay, that's what this is saying. Okay? So how do we find the charge using charge density and volume? Yeah? Yeah. Yeah. Big R is a constant. Okay? So if we went back to what Mark said at the beginning of class, what do we need to know about charge density and volume in order to find charge? Yep. No. How did you mathematically find? You had the charge length, the charge density, and you had the length. What did you do to them to get the charge? You multiply them, all right? So it's the same idea here, except we're going to do it in small portions. We're going to say that dq, or a small charge, is equal to, well, this charge density rho multiplied by small volume. And the volume is a function of R. So imagine this sphere, like an onion. And this onion only exists because of all the peels that make it up. Each onion peel is actually very thin, but it's just that when you add a whole bunch of thin layers, right, you get this whole thing called a sphere. Correct? Not correct? Yeah. So what is a small shell? What is the volume of a small shell of a sphere? Let me ask you a question here. We're going to draw a sphere, and it has another sphere inside, all right? And I'm trying to find the volume of this here. And this is the center. This is, let's just call this R1, and let's call this R2. How would you find the volume of the shaded part? Come out of the Melody and Marco, please. So how do you find the volume of a sphere? How do you find the volume of a sphere? You guys, someone else remember it? Mark, what is it? It's like 4 pi r. Yeah, 4/3 pi r cubed. Okay, Shani, continue. This is, which r is this? R2, okay. All right. That's how I find the volume of this shell here. But we want an infinitely small shell, right? A really small shell, so that this thickness here is dr. Okay? So if I want to do it like this, I can change this equation to 4/3 pi of R2 cubed minus R1 cubed, right? Or I can call this, if this is really, really small, dr. So it would be 4/3 pi r squared, because we accounted for those two dimensions. And that last dimension, the thickness, is going to be the small part of that thing. Yeah, no. Overall, you want it to be r cubed. There's one of them. Here's the other two. Okay. Okay, if we go back to here now. I have that dq is equal to the charge density. So that's 4 times 1 minus 4r over 3 capital R multiplied by the small volume of that small shell. I'm going to add up all those small shells afterwards. Okay, so the volume of a small shell would be 4/3 pi r squared dr. And if we want to add them all up, well, we integrate that, right? If we want everything, so we integrate it. So then Q is going to be equal to the integral. And from the radius of 0 to the radius capital R of 4 times 1 minus 4r over 3r times 4 pi r squared over 3 times dr. Yeah. So we wanted to find the volume of a really thin spherical shell and then multiply that by all the different r's in order to get the volume of the whole thing. Okay, so we find the volume of a small part of it, which is this, right? Except that because we're talking about the third dimension, we need to have the third exponent of the radius. Okay, two of which are accounted for because it's a circle. It's like a thin spherical shell, right? And then if you have the volume of a thin spherical shell and you multiply it by all the different layers of that onion, right, which has a thickness of very thin things, right? Then you're going to get the total volume of that object. Now it's just a matter of evaluating. Yeah, Brahman. The thickness of it is dr, and the volume of it is 4 pi r squared, or the surface area, if you want to call it the surface area of it, is pi r squared. Pi r squared over. Yeah, exactly. Okay. I won't solve this integral because it's very straightforward. It's if you distribute everything and take out the constants, you should have q is equal to the integral of some constant. Let's call it constant. What do you want to call it? Give me just a name real quick. R A B A. Let's go ahead. Some constant a. So that's a multiplication of all the constants in there. All right, between 0 and r, and then the variables are going to be r squared minus 4r r cubed, sorry, dr. Okay, and a is a multiplication of all the constants. So, yeah, shiny. Yeah, yeah, because that's a constant. Okay, I'll let you solve this on your own time, or you can do it now actually, because I have some problems that I want you guys to work on. Okay, so once you're done this, go to Moodle. There is a problem set called charge density. And I want you to try some of the problems. I'll give you guys 20 minutes to work on that. All right. And ask me any questions if you don't understand. Okay. So let's take 20 minutes to work on those problems. I'll give you guys a 5-minute break after that. Then we'll do the second part of today's lesson. When you have a sphere, the way you get a sphere is by, like I said with the onion, you have all these concentric spherical shells, right? It's actually, you have to think of it as the area or the surface area of each shell multiplied by the thickness of the whole sphere to get the volume of the whole sphere. And the area of one of these spheres is not 4/3 pi r squared, it's 4 pi r squared. That was the formula that you need to know for the area of a sphere, right? I made a mistake, I said 4/3 pi r squared. So it's actually just 4 pi r squared, and that's the area of one of these spheres, right? And then multiplied by the thickness, which is dr, will give you the thickness of that sphere. Yeah. The area of a circle, yes, but not the area of a sphere. Yeah, this, you have to consider this as a sphere, not a circle. Do you know the difference? Like maybe my exactly. Yeah. Okay. So when I was doing my calculations here, it should have been 4 pi r squared, not 4 pi r squared over 3. Okay, so that's my mistake. Okay. What I want you guys to do is, I'm not counting this or anything like that, but I'd like you guys to do it for next class, and I'll correct a few of them. Finish this this document, the charge density ones. Don't do number 3 and 4 because we haven't done voltage. And next class, I'm going to just correct a couple with you guys and show you the whole procedure so that everyone's on the same page with that. Does that sound good? Okay. Please practice, keep up with this stuff. The material is just tumbling forward now, okay? The next few weeks in this course are going to be quite intense, right? So it's important to keep a regular pace going. All right. Once you've done that, I want you guys to pull out PowerPoint number 6 because we're going to move on to the next topic. So here we're going to talk about electric fields produced by parallel plates, okay? And this is a very useful invention that we came up with. It just so happens that a lot of what you guys use and a lot of what you guys see uses the electric field generated by parallel plates. Let me give you one really clear example. What's that over there on the board? What is that a picture of? Yeah. Yeah, exactly. What is it? I guess so. He's right. No, it's not a spectrophotometer. That's something else you did in biology. It's like a gel. It's a gel. What's it called? What kind of gel? Yeah, nice. There is an electric current. To make the DNA move, okay? Yeah, getting closer. It's called a agarose gel electrophoresis. Okay? You guys, well, yeah, you should know that. You did it last year as a lab. That one I expect you guys to know. It's an electrophoresis gel. And what could you tell me about DNA? What is DNA made of? There's 3 parts to one nucleotide. I'm asking you guys to reach back. Your knowledge that you learn is not meant to be specific to a course. You're meant to remember it for the rest of your life. Or at least not half a year later. It is not even that long ago, yeah. It's definitely not. It's the opposite. The amino acids, those make up proteins, not DNA. Yeah, Marco. It's not made up of RNA. Yeah? They're made up of nucleic acid. That's what the Na stands for in DNA. Yeah, okay, yep. Okay, there's a base, all right? There's a nitrogenous base. That's one of the parts, right? Name me an example of one of the bases. Yeah, what are they? Yeah, okay, very good. ATCG. And then they base pair with another one. So you guys remember that T pairs up with A, C pairs up with G. Yes, please tell me you remember that. Okay, good. But that's not it, right? So let's say we had like this. This is T binds with A, C binds with G, G binds with C. All right, okay, that's all nice and dandy. That's the bases that are connecting the 2 helixes of the double-stranded helix. But what is this part of the DNA made of? So you talked about the base. There's 2 more parts that we're missing. There is, what does DNA stand for again? Deoxyribose. What is ribose? Oh my lord! Oh dude. Anything ending in ose in organic chemistry is what? Like glucose and fructose. Is that sugar? Okay, so there's a ribose sugar. Oh guys. Woo! So base. plus sugar. And now there's the one more part, and this is the most important part that I need to mention. No. What is it? Phosphate. Yes, absolutely. Phosphate. Woo. When you guys did chemistry, if you guys remember your chemistry, what is phosphate? P? That's not phosphate, that's phosphorus. PO4, 3 minus. Okay, there is still faith in humanity. All right, there is this whole backbone here is made up of phosphate. So it's a sugar attached to a phosphate, attached to a sugar, attached to a phosphate, attached to a sugar, attached to a phosphate. So DNA as a whole, if there's a bunch of these phosphate 3 minuses, DNA as a whole is what? Yes, negatively charged. Okay, woo, okay, all that. All right, so then if you apply it, so here's the electrophoresis gel right over here. All right, and then in these little wells, I don't know if you guys remember this, you are injecting the DNA. All right, and then in this gel, there's 2 rows of them, so they're down there as well. And then at a certain point, you turn on this machine, and your DNA flows in the downwards direction, or not the sideways direction, the downwards. Eh? Well, now it's not erased. Oh, that's fine. Okay, so that erases everything. So the DNA migrates in that direction. All right. That means that if you're applying an electric field and you're pushing negatively charged DNA, what would you say is at the bottom here? What charge is at the bottom here? Positive or negative? Positive. And negative up here. Okay? So you're turning on this electric field and your DNA is migrating downwards. Now, if there was just a charge here, okay, oops, let me erase it again. And now I don't know what. If there was just a point charge, a positive point charge here and a negative point charge here, how would the DNA migrate through this gel? Like if I had a piece of DNA here, where is it going to go? Towards the plus sign. And then what about the one here? Towards the plus sign, towards the plus sign, towards the plus sign, like that, right? That is not a very useful gel, is it? You want them to go parallel. So what you're going to do is you're going to create a parallel plate electric field. You're going to have 2 plates, apply an electric field that's very uniform across these 2 so that every strand of DNA flows in a parallel line. Okay? And that allows you to characterize the sizes and the fragments of your DNA. Most of you in health science. Yikes. All right. Another really useful example of a parallel plates is in those, who watches like Grey's Anatomy or Nurse Jackie or BR or any of those emergency shows. What you'll notice is whenever someone's dying, they take out the paddles and go woo, and then they shock you. Those are actually parallel plates, right? And what you're doing, not when you're rubbing them, but when you're shocking the person, you're applying an electric field through the person from one plate to the other plate, right? And that sound that you hear, that is you actually charging those plates. So you're turning on this machine and it's sending a whole bunch of charge. And like our electricity plugs here, they don't actually provide a lot of charge. But if you were to collect that charge over a certain period of time and you discharge it all at once, then that's actually a very big charge, right? So if you plug your finger in, you might hurt yourself. You're probably not going to die. Don't do it. You're probably not going to die. You'll hurt yourself because the current coming out of that is the charge per second coming out of that is actually quite slow, right? So what these paddles do is instead of when you're getting these slow charges, it's like a dam, right? So it's like all the charges go and they stop here and they collect and collect and collect and collect. And when you press the button, you release it and all the charges go at once. You're making a huge current. That's called a capacitor all at once. And that shocks the person. And the purpose of that is to refibrillate defibrillate the heart to get it to go back to a normal beating rhythm when it's not beating. Most of the time in the shows, they do it like 4 or 5 times. In reality, they do it once. If it doesn't work, move on. Yeah, there are other things to discuss. Okay. There are other things. For example, the camera flashes that you guys use, those are parallel plate capacitors. We'll talk about those later. But essentially, these things are everywhere. Okay? Who is old enough to have a TV that wasn't this thick? That was like this thick? Who remembers having TVs that are this thick? All right. Believe it or not, that used to be like the only way you can have a TV. Now you can a TV apparently. It fits in my hand. I can move it up and down. There's no wire attached to it. It has access to all of the information in the world. It's crazy. But back then, the TVs were a lot more complicated than that, or a lot more simple for a lot more complicated technology. And we'll talk about that today. So the topic is parallel plates and the electric field generated by a parallel plate, right? So there's your parallel plate. There's your other parallel plate. This one's positively charged. This one's negatively charged, right? And then you have these, because you have positive charges and negative charges, you have an electric field leaving the positive charge, entering the negative charge, okay? So they go like that, right? I'm going to ask you guys a question now. If I were to show you, if I were to choose just one of these charges, I'm going to choose this one. If I chose just that one charge, what does the electric field coming out of that one charge look like? We talked about what an electric field looks like for one charge. Repeat it to me so that I know you were listening last time. Now it makes sense, but you can't remember fast. Come on. Ronnie. It goes out in which way? Out of the positive, but in which direction? Every direction, all right? So it has one going upwards, and that's the one I chose to draw there. But there are others going in these directions. Why, oh why, do they not matter? And that why is it that all of these lines here are parallel and there are none that are not parallel? What do you think? Yeah, absolutely. So you can summarize it all with one word, and that one word being vector, right? So if there's a charge applying an electric field in that direction, there's going to be another charge applying an electric field in that direction. And what could you say about this electric field and this electric field? What's that? They cancel out, not entirely, but their horizontal components cancel each other out, and they're producing only a vertical component. All right? So that's the advantage of having these parallel plates. It only works if the plates are parallel. If they're just off parallel, then you get weird electric fields, and it no longer works the same way. Okay? So here they are. And we're going to talk a little bit about voltage, but there's going to be a whole lesson on voltage later on. So you'll understand a little bit more now. Essentially, voltage refers to as the difference of the charges between the two plates. All right, so this is going to have a Q. We're going to call that Q1. This is going to be Q2, right? And that's going to produce some voltage, and that's going to produce some voltage. And delta V would be V, if this is V1, V2, it would be V2 minus, would be V2 minus V1, okay? V2 minus V1, okay? And in order to calculate that electric field, we need two things. So if I increase the voltage, if the charge difference is really different for the two plates, right, am I going to have a stronger electric field or a weaker electric field? If I increase the voltage, you have a stronger electric field. So that means the electric field is directly proportional to the strength, the voltage strength. All right. What if I made the distance between the parallel plates bigger and smaller? When is the electric field going to be the strongest? When the distance between the plates is the least, exactly. So I have this relationship here, which says that the electric field E is proportional to the voltage, right? It's proportional to the voltage and inversely proportional to the distance between them. I have another relationship to talk to you guys about, and that's the area of the plates. If I have a bigger plate and the same charge, how is the electric field going to be different? So let me just ask you one more thing before we delve into that. The higher the charge of the plate, what happens to the electric field? Does the electric field go up or down? Up, okay? So the electric field is proportional to the charge. All right, so let's say I have 50 charges on a plate. Is the electric field going to be bigger or smaller on a bigger or smaller plate? If I have a big plate and I have 50 charges versus a small plate that has 50 charges, which one's going to produce a stronger electric field? Smaller. So therefore we know that it's inversely proportional to the area of the plate. Okay? Epsilon is a constant of permittivity of free space. We'll be using that a little bit later. So epsilon is a constant. So far, so good? Okay, shiny. Say that again? Because two plates, one have a positive charge, the other one's going to have a negative charge. The field goes from positive to negative. No. Yes, Ronald. We'll talk about that later. It's going to come in maybe 3 classes from now. Okay. It basically has to do with the calculus of it. We're going to do integral. So ignore that for now. Yes. The other way around. Go back to your notes. You'll see it. It was just convention, positive, negative. All right. Let's go back just real quick. If I were to place a positive charge here, okay, so we have this plate, it's fully positively charged, and there is a uniform electric field, all going from the positive to the negative. If I placed a proton right there, if I placed a proton right there, what would happen to it? Yeah? It would go to the negative. It would move. If it would move and it was stationary, that means there was a acceleration. If there's an acceleration, that means there is a force. Okay, so there is a way to calculate that force as well. And that force is Q times the electric field, right? And we learned that before. Remember, we saw it this way. We said F over Q is equal to E. Do you guys remember this? F over Q is equal to E. That was like 2 classes ago, maybe, or maybe it was last class. We know that, right? And Q is going to be the charge that we place in the electric field. And if we place a charge in an electric field, it's going to submit to a force F. Okay? And of course, we know that there is an acceleration. So any force has an acceleration we call ma. That's Newton's third law? Yeah, third law. Second law? I can never remember the name. Third is, you're right, third is actually second is FMA. Yeah, you're right. So far, so good? Should we do this now? Let's just do these 2 simple problems. All right. Essentially, we have to remember that the electric field is equal to voltage divided by the distance between them. Okay? So that's what you're going to need to do in this problem. So the capacitor inside your digital camera has a potential difference of 330 volts. The distance between the parallel plates inside the capacitor is 9 millimeters. What is the electric field between the plates? Right? So it's very straightforward. So E is equal to voltage, which is 330 volts, divided by 0.09009 meters. Someone just punch that in real quick in your calculator. You got something? What are the units? Or how do we know our units from electric field? Someone else? What's our unit for electric field that we learned last class? Markup? Newtons per coulomb. Okay? Same unit. Okay? Next example. A proton is accelerated from rest from a positive plate inside a parallel plate capacitor. The plates are 3 centimeters apart and are connected to a 110 volt source. Find its final velocity when it collides with the negative plate. So I'm going to draw a drawing here. So here are your plates, right? And the proton, so there's a positive side and a negative side. There's a proton here, right? And then you apply this voltage, right? Which is written right here. The voltage is 110 volts. When you apply this voltage, what's going to happen to that positive charge on that plate? Going to, yeah, just move from one side to the other. The acceleration is going to be quite intense because we're talking about the proton, which is really small, right? So what we need to do, if its initial velocity is, what is its initial velocity if I just place it there? Initial velocity would be 0 meters per second, right? And I'm looking for its final velocity, okay? Which relationship in your, now you have to remember back to mechanics last year. If you have to remember your projectile motions and all things like that, how do you relate initial velocity and final velocity? Yep. Close. Melanie. Okay. We have the initial velocity. You said it's 0. We have the distance that it has to travel because it says that these plates are 3 centimeters apart. So that's how far it needs to travel, right? And we need acceleration if we're going to find what the final velocity is. And acceleration is a part of the force formula. So let's go there. Force is equal to mass times acceleration. What else is force equal to? If we went back, what's that? Electric field times Q. Now, what do we know about electric field? Electric field, if we look here, is what? V over R. So Q, V over R. Now we're trying to solve for acceleration. What's the mass of a proton? It's on our quiz today, wasn't it? Mass of a proton is 1.67 times 10 to the negative 27 kilograms. The charge of a proton is equal to 1.62 times 10 to the negative 19 coulombs. That's just a formula thing that you need to plug in, blah, 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 blah. Plug it in, give me a number. Tell me what VF is. Which one? 27? The mass is -27, -27. Here's the charge I was replaced there, and it's talking about a proton. So a proton has a charge of 1.6 times 10 to the -19, and a mass of 1.67 times 10 to the -27. We're doing really well, guys. Let's keep going. We don't need it. We're actually going to use this is equal to this to solve for acceleration. Oh, there's a button that could turn this into an eraser. That's so cool. Oh, that's going to save me so much time. And that right clicks. How does end sense? Who has an answer for me for velocity? It's going to be a fast velocity, yeah. That makes sense. What number would not make sense? Negative? You're right. I mean, if you did a square root, so the answer actually could be negative. If it were greater than 3 times 10 to the 8 meters per second, what does that mean? What's 3 times 10 to the 8? Yeah. Yeah, it can never be faster than light, okay? We're never going to make it so that anything travels faster than the speed of light. Yeah.
But what if like in a circle where you want an acceleration of like 1 times 10 to the 30
It doesn't matter. That's the acceleration, not this velocity.
Yeah, but in 2
So
seconds, you're like faster than the speed of light.
So that means it can't. It'll top off in less than 1 second. Yeah. You talking about the quiz? Talking about the quiz? The answer is big in the quiz. So if you got something to the 35, that sounds about right. Are we okay with this? This is the same exact question. Let's not do it. I want to move on to something called a cathode ray. This is how TVs work. Imagine I had 2 parallel plates like this. They're charged. All right. And there is an electric field in these plates. What direction is the electric field in this case? Which direction? Up or down? Come on, guys, wake up. Up. All right. Now let's say I shot a charged object into them. What's going to happen to them? It's going to, well, it depends on the charge. Yeah, it's going to do that, but it also depends on the charge. So if it was positive, it will go towards the negative. All right. If it was negative, it will go towards positive. So let's say I'm shooting a proton into this chamber that has an electric field. And what's going to happen is as soon as it enters the electric field, what's going to happen to it? It's going to deflect and it's going to go like that, right? That shape, what does that shape look like? If I were to turn it upside down. Square roots. I'm not looking for a function. I'm looking for another physical thing that you might have learned last year. Looks like a projectile, exactly. All right, except instead of it falling down, it's falling up, right? And that's the same as in gravity, right? In gravity, you throw an object, it's in a gravitational field, so therefore a gravitational force acts on it. Here, you're shooting a charge in an electric field, so an electric force is going to act on it. Yes. Yeah, absolutely. Yeah. So, okay, so now if you look at this cathode ray, right, it's got, I'm going to try to improvise here with some flat objects, right? So if I go like this, all right, and the object is going here, so it's going to get deflected up and down depending on its charge, all right? Everyone's okay with that part? All right, so you can regulate the voltage of this depending on how much you want to deflect it, and then it goes into another parallel plate, all right? And this time the parallel plate is like this. The parallel plate's going to be like this, and the charge is going through here after it was up and down deflected, and now it's going to be side to side deflected. So with the up and down deflection and the side to side deflection, and you controlling the voltages very precisely, you can see exactly where that ray is going to go on a two-dimensional flat screen, right? And so if I go to the next slide, if I go here, you can see this is a gigantic cathode ray tube, and this part here is the TV screen, right? And then in here it's getting deflected left and right, and forward and back, and it's going to land on different parts here. And they do this so fast with particles that your eye can't determine that it's all happening one at a time. So what happens after a certain number of these things happen, you see an image that moves, right? And look how gigantic this thing is, right? So you have to imagine that this is just the screen, right? Everything else is in a box that you're looking at, and that's the size of it. This is gigantic, massive, ugly furniture thing that sits in your house, and you watch TV from. Quality is really crap, but the science behind it is actually quite ingenious, right? For someone to have thought to do that, okay? So takeaway message from this is, if I have parallel plates and there's an electric field between those two plates, I can I can shift particles in there like I do in projectile motion. Okay? And so that's what this is here. So look at this problem, right? You have this electron that's on the negative plate, right? So these are the negative charges. And you turn on the electric field and it's going to accelerate this way. This is the problem we just did before. Then it enters into this electric field, right? And it's going to get submitted to an acceleration, right? Kind of like in gravity, the acceleration is what? What is the acceleration for gravity? 9.8 meters per second squared. Here, there is no constant because we can modulate the electrical acceleration by increasing or decreasing the voltage, right? So if you calculate the acceleration, you basically have a projectile motion problem with acceleration being whatever you calculated from before. So we went back. If we go back here, we calculated that the acceleration is equal to QV over R times M, right? So this is the charge of a proton, mass of a proton, and if we know the voltage and the distance between the plates, then we can calculate the acceleration that particle would feel as it goes into this electric field. Okay? If we have acceleration, then we just have to remember our formulas. I don't know how you guys have them written down. This is how I remember them. Does this look familiar to you? Or some of you might remember it as delta y is equal to 1/2 AT squared plus VIT or something like that. I don't know. Everyone's got a different way of writing these formulas down, but they're the same ones. They're just written in different ways. And if you have the A, you can apply all these formulas, right? You can even apply the VF squared equal to VO squared like we just did. You guys understand what I'm saying? Let's do this one problem and then we'll go. Okay? So let me just preface this problem by drawing an analogy. If you have a table here, all right, and you roll an object off of it, its initial velocity is in which direction? No, of my object that I'm rolling off a table. So there is an object that I'm rolling. Yeah, it's positive x only. There is no initial y velocity. And then after it reaches the end of the table, it's going to start falling down like this. Oops, it's going to start falling down like this. That means its initial y velocity is what? 0, and its final y velocity is some negative number. What is its x velocity? Does its x velocity change throughout this? No. All right, and this here, this height here of this table, that's going to be its y displacement. All right, and that's what this first question is asking. It's asking you for the vertical deflection, which is the y displacement of this projectile motion. Okay, start working on that. I'm going to pass around. Once you're done, show me your work. Otherwise, otherwise you're working up until 12 o'clock. And then after that, I'll wish you guys a good weekend. Next week, we're going to try to practice a few more of these at the beginning of next class, but we have to move on to some other new stuff.